So yeah, you just need to see if there's an H moving around, and that's how you figure out if Bronsted-Lowry is at play. Second inquiry question is using Bronsted-Lowry theory. So Bronsted-Lowry is the proton acceptor, proton donor stuff. That's what you need to keep in mind while we're doing this. First part of the inquiry question is talking about pH and how we measure it. So we've already talked about indicators and litmus paper. You'll have to do a prac in class with measuring pH, but the main way to do it and do it semi-accurately, or the most accurately that you would get in a school lab, is using a pH probe. pH probes are super cool. You have a lot of things going on with pH probes. You've got really cool curves that you can make with putting a pH probe in during a neutralization reaction. But yeah, they just spit out a number and tell you the pH, which is always fun. You need to calibrate it, obviously, but you calibrate it using a buffer liquid. But yeah, you just use it to measure pH, which is cool. So that's one of the dot points. Next dot point is all about what is pH, how do we calculate it, all that fun stuff. So what is pH? pH is a measure of hydronium ion concentration. Hydronium ion concentration is water plus a hydrogen, and to me in my head, I know it's not the same, and it's kind of not good to tell you guys this, but in my head, I think of pH as a measurement of hydrogen ion concentration, not hydronium. I know it is hydronium, but the H in pH just tells me it's hydrogen, and I kind of just go with it because they're quite interchangeable. But when you write a reaction and when you write your working out, you have to have it as hydronium. But like, don't be like, where's hydronium from? I've never heard of that before. It's just hydrogen. Like, you don't have to overthink it. It's just hydrogen, but added onto a water. But yeah, it is a scale that's an inverse logarithmic scale, and it means that lower pH, so your super small ones, your like 0.1 pH or 0 pHs, if it can even go down to there, those really low numbers means there's a high amount of hydronium or hydrogen. And that means that it's acidic, because if you remember, hydrogens are your protons, and acids are your proton donors. So if you've got a high amount of hydrogen, that means you've got a high amount of donors. So in the logarithmic scale, because it is a log thing, the change of pH of 1 is a 10-fold increase or decrease in hydronium ion concentration. So that gives you an idea of how severe, not how severe, but how pH works. This is how you calculate pH. It's minus log, and then you put your concentration. You can also calculate pH from POH, which is just minus log hydroxide concentration. But pH and POH, if you add them together, they should equal 14. pH plus POH equals 14. So you can use pH or POH to find the other by minusing from 14. If you want to find the hydronium concentration from pH, what you need to do is do 10 to the minus pH, and then you get the hydronium concentration. Same with POH. If you put 10 to the minus POH, that'll give you the hydroxide concentration, which is sick. And like in the HSC, you're never going to get a question that's just like, here's the hydrogen concentration, what's the pH? Like, they're never going to be that nice to you. Hate to break it to you. They're always going to add a little extra step, something like a dilution or figuring out how many moles it is. So to do that, you need to remember your normal skills. So your normal molar ratio skills, but also C equals N on V. So concentration equals number of moles over volume. And then number of moles equals mass over molar mass. And if you know all of those, you should be good to do the next round of calculations. So here's a bunch of chill calculations. If it says what is the pH of a solution with a hydrogen concentration of 0.01, what you need to do then is do minus log of 0.01, and then you get your pH, which should be 2. Second question, what is the pOH of a solution with an OH of 0.000316? Same thing, you're looking for pOH, so minus log of the OH concentration, which is given 0.000316, and you're given a pOH of 3.5. Cool. Then what is the pH of a 0.23 moles of HCl? So HCl, hydrochloric acid, is a strong acid, so we can assume that the hydroxide or hydrogen or hydronium concentration is the same as the concentration of the acid. So you go minus log 0.23, and bam, you get a very low 0.64. For the pH of 0.1 molar NaOH, sodium hydroxide, same kind of idea. You just chuck in the 0.1 into the minus log to find pOH, and then you minus from 14. So minus log 0.1 gives us 1. That's our pOH. To find pH, you go 14 minus pOH, which is 13. Then for question 5, concentration of nitric acid if the solution has a pH of this much. To find a concentration from a pH, you just go 10 to the negative pH. 10 to the negative 5.73 gives you super small number. But yeah, same thing for the other one. So the really small number for question 5 is like 1.86 times 10 to the negative 6. The very small number for question 6, we're given the pH of a basic solution. So we find the hydrogen, we find the pOH first, sorry. So pOH will be 14 minus pH, so that's 4. Then we go 10 to the negative 4 to find the hydroxide concentration. Yeah. There we go. So hopefully that's made sense. Some of it probably didn't make sense because I put this slide next door and not beforehand. But you got to know strong acids versus weak acids, strong bases versus weak bases. How you do that is you memorize it. If I'm going to be completely honest, you need to remember which are the common ones. The more you expose yourself to module 6, the more you'll realize which are the strong ones and which are the weak ones. But like right now, you probably haven't really done module 6 yet, so it'll be fine if you don't really know. But what to know is that strength of an acid is associated with the degree to which it ionizes. So more ionization means it's stronger. Strong acids like hydrochloric acid, they ionize completely. So they don't have an equilibrium arrow. They have a full arrow. They go straight from hydrochloric acid, and all of that hydrogen in the hydrochloric acid becomes hydronium. For weak acids, they do not ionize completely. So they exist at this equilibrium, and we need something called Ka to figure out the exact hydrogen concentration or hydronium concentration. So same kind of thing with bases as well. But if you compare equal concentrations of strong acids and weak acids, you'll notice that the strong acid has a lower pH because it has more hydroniums because it had more hydrogen ionizing. If it has more hydronium, has a higher concentration, lower pH, more acidic. So usually strong acids have a lower pH, and then weak acids are the ones that end up being buffers and have a midish pH. common strong acids and base. Oh, and I forgot to say that also applies for bases. Strong bases dissociate completely. Weak bases exist in equilibrium, just like the acids. But yeah, so strong acids and strong bases. Here's a list. Your group 1 hydroxides, they are your strong bases. Your strong acids are, there's not really a pattern to it. It's kind of just like the common ones. So hydrochloric acid, nitric, sulfuric, phosphoric. Sorry, there was a truck just passing my house. Phosphoric acid, hydrobromic acid. Those are your strong ones. Have to remember those. And then you've got weak acids, which are usually your organic ones. Carbonic acid as well. Yeah, and then weak bases, common, like the most common weak base ever would be ammonia. But like, to be honest, there's not really a fun little pattern to remember this like there is with solubility rules and like NAG/SAG. For this, honestly, it's just remembering it, which is such a trek. But the more you expose yourself to questions, the more you study hard, the easier it is to remember. Cool. Okay, so the action of acids and bases in water, this is something you need to consider when like drawing out any dissociation equations for acids and bases. But in water, what happens is the acid donates its proton to the water. So it becomes an anion plus hydronium. So the acid donates it to the base, which in this case is water. For bases, you have a base, which is just like that B, and it takes a proton from the water because it's a proton acceptor. So that's how it becomes BH plus OH minus. So yeah, back to Bronson-Lowry theory, it's just about which one donates, which one accepts. Water acts as the acid when it acts with a base in water. Water acts as the acid because it donates its proton to the base, which accepts it. We have some other terminology that we have to get used to, which is conjugate acids and bases. So if you have a base plus an acid, the base, after accepting the proton, so let's say the base is the water, once it's become hydronium, the water has acted as a base because it's accepted a proton. Once it's accepted it, it's no longer a base, it's a conjugate acid. Once the acid has donated its proton, it's no longer an acid, it's a conjugate base. Same kind of thing, when a base is just as its own, it's fine. Once it's accepted a proton, it becomes a conjugate acid. Once an acid, which in this, like the second case here, that one, the acid acting in this situation is water. Once that has once that has donated a proton, once it's donated a proton, it has become the conjugate base. Now, the strength of conjugates is something else completely. So the strength of conjugates is kind of an inverse relationship. So if it's a strong acid, like let's say hydrochloric acid, its base, its conjugate base, so just chloride ion, that conjugate base is weak compared to the acid. And yeah, if it's a weak acid, it's also a weak conjugate base. But yeah, if it's a strong acid, it has a really weak conjugate base. It's just how it works. So that's the strength of conjugates. Now, I did say a while ago that I'd get back to salts. And salts, you can have acidic and you can have basic salts. You can also have neutral salts. But the way to figure this out, there's like a lot of text on this slide, but really there's a really easy way to figure out if a salt is acidic, basic, or neutral, and it's to figure out what made it. So let's say we have sodium sulfate. Sodium sulfate is the salt. You think of what was the acid, it would have been sulfuric acid. What was the base? Probably sodium hydroxide. So we have our acid, we have our base. We need to figure out if it's strong base or weak base. Both of them are strong. Sulfuric acid is a strong acid, sodium hydroxide is a strong base. So since they're both strong, it becomes neutral salt. Now, if we have, let's say, acetic acid with sodium hydroxide, so we end up with sodium acetate as our salt. Acetic acid is a weak acid, but sodium hydroxide is a strong base. So it ends up being a basic salt because the strong base kind of overpowers the weak acid, and then it goes too far and it becomes a basic salt. You can also think of it in terms of the conjugate acids and bases, but I just find that hard to wrap my head around. So personally, I just go for the what made it kind of deal. But we'll talk through the other one. So yeah, if the conjugate base, if you have a conjugate base of a weak acid, it'll form a basic solution because it can act as a weak base. And if you have a conjugate acid of a weak base, then it can produce an acidic solution. But again, just figure out what made the salt. Use the two ions to figure out what made the salt, and then figure out if those were strong or weak. And if they're both strong, you're neutral. If they're both weak, you're neutral. If you have a strong acid and a weak base, so like hydrochloric acid and ammonia, strong acid, weak base means an acidic salt. Strong base, weak acid means a basic salt. Like this. I chose great examples. I completely forgot making this slides. So I didn't realize I'd use the exact examples, but fun time. Strong acid, weak base means acidic solution, which is what's going on here. Cool. So final kind of thing for this dot point are your protic things. I think that's just a funny name for the slide, but your protic things are, oh no, this is not the last thing we have to do for the next one. Kind of. Sorry, I'm just like looking ahead. So your protic things. You've got your polyprotic, which means you can donate multiple stuff. So for example, monoprotic is like hydrochloric acid. You donate one proton, whereas diprotic, you have two protons that you can give out. So just like sulfuric acid. Then phosphoric acid has three. It's triprotic. You can give out 3 whole protons. That's what polyprotic means. Amphiprotic means that you can donate or accept. So this is what I was talking about with sodium hydrogen carbonate. It can act as a a proton acceptor or a proton donor. So if we have the ion bicarbonate is what is amphiprotic. So we have a bicarbonate ion and it's added to hydronium, which represents the acid. That hydronium is the acid, so it donates a proton. So then it makes carbonic acid plus water. And then if it's a base, sorry, that was a fly. If there was a base, you have I forgot the word. You have bicarbonate ion plus hydroxide. The bicarbonate then acts as an acid, donates its proton to the base to make water and carbonate ion. Okay. Other thing, strength we've already talked about, the degree of ionization. Concentration is something that you should already know. It just refers to how much is, like, how many molecules in that volume. If it's super concentrated, that means that you've got a lot of particles of the acid in there. If it's not concentrated, you don't have a lot going on. These are really good diagrams because it shows strength and concentration. You can see the strong concentrated, all the particles have separated and there's lots of them, whereas strong dilute, there's not many of them, but they're all still separated. Weak dilute, there are some that are still together, some that are separated, which shows that degree of ionization. And weak concentrated, same degree of ionization, there's just more particles. So it's a really good representation of strength versus concentration. Now, a trickier calculation that you might have to do is calculating the pH of resultant solutions. And for this, you've got to work out the limiting reagent. So in my personal experience, I've just hated limiting reagents. I understood it towards the end of year 11 chemistry, but I just never understood it while I was doing it. And I feel like that's a kind of a common theme with chemistry. You kind of just don't understand limiting reagents until you finally like have a click moment and you're like, oh yeah, limiting reagents make so much sense. Yeah, so if you're not cool with limiting reagents, maybe brush up on that before trying module 6. But for limiting reagents, what you do is you figure out the concentration of, like, you figure out the number of moles of hydrogen and the number of moles of hydroxide. Whichever has the least amount of moles, that's your limiting reagent. Once you find the limiting reagent, that's all that's going to react. So you find out what's left over of the other one. And whatever is left over of the other thing, the non-limiting reagent, since it's mixing acids and bases, so since neutralization would have occurred, the pH would be neutral. So the only thing that's affecting pH would be the leftover once you've reacted all of the limiting reagent. So you use the leftover to calculate pH. You also have to take into account changes in volume. So if you're adding 150 milliliters of one thing to 150 milliliters of the other thing, you no longer have a concentration that you originally had because now you have a different volume. So you usually end up with a lower concentration because you have a changed volume that's bigger. So remember that because that's something really easy to forget. And yeah, don't really worry too much about weak acids because there's the extra step of Ka that you'll need to do, and that's kind of a pain to put in with the rest of the stuff. But yeah, convert moles into concentration, then find pH. So it says 250 mils of nitric acid at this concentration is diluted to 500 and of KOH, a strong base. What is the resulting pH? Cool. So what you do here is you write out your equation first of all. You have nitric acid plus potassium hydroxide makes potassium nitrate and water. Then you need to figure out the number of moles of each. So you start off with the acid, which is 0.25 liters, because concentration is moles per liter, multiplied by 0.33, and then you find the number of moles of the base. Then what happens is that you see that the limiting reagent is the base, which only has 0.05 moles. You have 0.05 moles being used up, so you take that away from the 0.825 of the acid, and you end up with 0.0325 moles of acid after neutralization occurs. So that's what we'll be using to find the pH. That's the number of moles. We need to find the concentration before we can put it into our pH calculation. You have it in moles. We want it in moles per liter. So C equals N on V. We put moles on the top, so 0.0325 goes on the top, and V goes at the bottom. Your volume will be 500 plus 250. It'll be 750 mils because you are adding them together. It becomes new volume. So it'll be 0.75 because we want it in liters, and that'll give us 0.043 moles per liter. Then that 0.043 can go straight into our minus log, and that'll give us a pH of 1.36. Now, the hardest step in that was accounting for the change in volume. Everything else is stuff that if you are really good with your moles, you wouldn't have too much trouble with because it's just a 1-to-1 ratio. So finding the limiting reagent is quite simple. You just go which one was limited. Yeah, which one had less amount of moles. But if it changed the molar ratio to, like, let's say it was with sulfuric acid instead of nitric acid, it'll be 1 sulfuric acid for 2 of the potassium hydroxide. So that change in molar ratio would have changed how we did the limiting reagent, which would have made it a little bit trickier. But yeah. This is a simple multiple choice question. Which beaker contains a strong acid? You pick whichever has ore dissociation, and then you pick which one is concentrated. So B is our answer because all of it's dissociated, and there's more particles in it than B, which is also ore dissociated. Then this one says which is the conjugate base of the dihydrogen phosphate ion. So it's asking which is the conjugate base, which means that dihydrogen phosphate must be working as an acid. So it donates a proton. We look at what is the dihydrogen phosphate minus a proton. It's HPO4. So that's the conjugate base. Now on to the